Oh, thanks a lot, John. That was a great introduction. Thanks for having me. Okay, so as you can see from the title slide, I'm going to be talking about future polygeneration systems. John, can people see my mouse? Is that?
Yeah, we can see your mouse.
All right, I'll use that then. Great. Okay, so yeah, I'll skip the about me slide, but so we'll go on to my generic introduction slide, right? So nearly every introduction slide you'll see for a talk of this type will have, the bullet points about CO2 causing global warming, pictures of cuddly polar bears, pictures of trees, that kind of thing. Bonus points for citing the International Panel on Climate Change reports. So I'm going to kind of skip this part because I think that's pretty well known by most people, and I'm going to move on to something that's a little more local in terms of motivation, and that's what I call the Toronto problem. So this basically illustrates the major societal problem we have with clean energy. Okay, is that people want it, but they don't want to pay for it, basically. Either it's too inconvenient or too expensive. So here's an example. So here in the Greater Toronto Area, we're growing rapidly, and we definitely need power due to growth. Not just due to growth, though, but the aging of our power fleets. And people say, okay, well, if we're going to do anything new, it's got to be green, and we want green power anyway. And actually we have some legislation and some regulations, and essentially all of our coal power in the province is slated to shut down in 2014. It's it's almost, I think, 40% of Canada's coal supply would be shut down as a result of this, if it happens. That's the plan. We're all paying a higher tax right now to cover that cost. And they say, okay, instead of that, we're going to do wind power. So then they have this push to try to get more wind in the province to replace this coal. But even though they supported the wind turbines themselves, the people actually rejected the transmission lines. Okay, because for wind power, right, you need lots and lots of transmission lines. And if you've ever been around here, there are transmission lines everywhere. People are sick of looking at them. So we're actually right back to where we started. So at the moment, we've got nothing to go on in terms of growth. So this is just a great example of the problems that we're facing. And we put this in the context of what we call the triple bottom line of sustainability. So in my group, we try to look at the energy crisis from a systems perspective in the context of the triple bottom line of sustainability. So that means we want things to be sustainable in the sense that it's affordable, so it fits in the economics category. So that includes like job creation and profitability and uncertainty and risk and all that stuff. It actually is environmentally friendly in quantifiable ways. So particulates, land use, water, and of course global warming and smog and all that sort of stuff. And then the third aspect is society, which is equally important, if not more important, to getting something actually done, which is basically public acceptance, NIMBYs, that's not in my backyards, people that support something but just not where they are, and that sort of thing. So it has to fit in. It has to make sense from a business perspective. It has to actually be environmentally friendly, and people have to be okay with it. And that's a real problem. So fundamentally, what this presentation is going to talk about are certain enabling technologies. So these are technologies that I think are going to really change the way things we do from an energy systems perspective. All right, so these are technologies that enable new things that we're not doing right now, and how that is going to help us solve this problem, satisfying all three tiers. Okay, so the first technology I'm going to talk about is solid oxide fuel cells. For those of you not familiar, this is not like a fuel cell that you used to thinking about like for a car or something like that. So it's a very different kind of fuel cell. Essentially, you have fuel going in an anode, and this can be actually quite a large number of fuels: like syngas, hydrogen, methane, natural gas, all that stuff. And then we have air in the cathode. And basically the way this works is that they're separated by this solid oxide electrolyte conductor. So basically you have oxygen ions that, you have a free electron coming through your cycle, through your system. It basically hits the oxygen in the air, and that splits into oxygen ions. And these are conducted through. It's solid state. So it's more like electrons in a wire than it is diffusion, right? So what ends up happening is the oxygen passes through, but none of the other materials goes in either direction if it's properly made. And then so when this reacts with our fuel, depending on the kind of fuel, you get your waste product, and then the electrons are released. But now they have a higher energy potential. Okay, so that's basically the energy content now is in that electron, that goes to your load, and that drives your circuit. Okay. One of the so the reason these are special is, I mean, that's a different way of a fuel cell for working, but there's some key characteristics which really make it an enabling technology. So one, it's potentially up to high pressure, so these are in development up to 10 to 20 bar. It itself is about 50 to 60% efficient, which is good, but that's just one part of a system, so that's even better when you think of it that way. High temperature is good and bad depending on your perspective, but the real key here is that the outlets, it can be constructed so you don't have mixed exhaust. You actually have two separate exhaust streams. And well, I'll show you why that's important in a second. So here's an example of sort of a long-term, maybe 20 or 30 years down the road, way of doing bulk power from natural gas. Is that instead of combustion, okay, we're going to use like an SOFC system. So these would be banks of stacks of cells, many cells. Okay, and so your natural gas comes in your anode side, air goes in your cathode side. And what's interesting is you can get, depending on how you do this, 50 to 80% of the fuel gets used. Okay, what you're left with is your exhaust product, which is CO2 and water, and then your unspent fuel. So then you can do an oxidation step. So this would require air separation or some other means. But the higher you go here in your fuel utilization, the lower you need here. But essentially, you complete the fuel for heat. And what you're left with is just water and CO2. So you can recover this waste heat in the heat exchanger network. Here I'm showing like municipal hot water, but it's hot enough you can use steam generation for more power if you want. And then what you get is the CO2 water is relatively easy to separate. Like you can just use condensation, essentially, in flash drums just to get the CO2 out and the water out separately. So, and your airstream never mixes. So nitrogen never gets in and mixes with your carbon. And that makes it way, way easier to handle from a CO2 perspective. Okay. Excuse me. So what some of the key things here, very little energy penalty for doing the CO2 separation. You can get CO2 at about 100% capture at high pressure. Okay. The water you get is actually drinkable. There are people I've talked to that have drunk it. I wouldn't do it personally, but on the space shuttle they use actually a fuel cell, at least at one time, to produce water and energy at the same time. And you get extra power from your waste heat. So there's all sorts of places you can produce electricity. So a lot of interesting advantages here. And here's an example of, all the many different ways we can do this. Okay, so here's from natural gas, and this is a superstructure. So this is sort of a map of all possible processes that we're looking at. So there's different things you can treat the fuel with, different reforming steps and shifting. You can use coal and biomass, so you can do gasification, and there's different levels of hydrogen you can use and different kinds of cleaning steps. And how you complete the fuel. So we can use oxidation, which is sort of more futuristic, because we need this oxygen in an affordable way to get 100% carbon capture. But you can also just burn it too in a burner or gas turbines, depending on your fuel utilization, and then how do you treat that waste heat for more steam or hot water, right? So there's lots and lots of things we can do. And this is really cool because basically when you trace the carbon pathways, ultimately, if you go this route here, you can get essentially 100% capture if you sequester. So that's really the kind of cool thing. So here's an example with coal and natural gas, just showing you efficiencies here, higher heating value. So on the left side we have coal, the right side we have natural gas. And then here these green ones have capture, and blue has no carbon capture. So this is traditional pulverized coal with capture and without capture, and you can see like the drop is over 10 percentage points, right? That's a huge, huge impact of carbon capture, and that's using like solvents, right? Here's natural gas. Again, you get quite a significant drop. But with the fuel cell systems, right, first of all, not only is it more efficient, but the drop you get for adding carbon capture is minuscule. Okay, and what that means is that the CO2 capture part is easy. The system itself, it makes it is easy to do carbon capture because the fuel cell enables that ability, right? So that's the enabling technology. All right, on the natural gas side, here's your natural gas combined cycle, and then these are different forms of reforming. So I mentioned that we looked at different types, right? But all the way up to looking at 73, 74% efficiency. That is phenomenal. The state of the art's about 50. So that's some really incredible results from the efficiency perspective. From CO2, here we're looking at CO2 emissions in megaton per year for a 700 megawatt plant. Here's your pulverized coal when you add capture, even if you get 90% capture, your emissions actually only reduce by 80%. And that's because you basically need additional coal to make up for the power, the parasitic power required to do the capture, right? So it actually, even if you capture 90% of what you got going through your capture system, you actually have to burn more coal just to account for that. Okay, but with your fuel cell system, even without capture, it's still, 15–20% better just from the efficiency, and we can go down to zero, basically zero emissions. Same thing for gas as well. Okay, so that's what's really, really neat. And then water. So there's a lot more to the environment than just the global warming that we need to consider. Here's another thing. Because we're capturing water at high purity, we're actually have a net water consumption when we do carbon capture, because we actually capture water as a product, and it's ultra high purity. Okay, so it's when the systems are designed, you look at the impurities, and they're basically the same as on the bottle of Dasani's. Actually, I kept that on my desk as comparison when I was doing these studies. So this is in this case we're using no dry cooling. So there's more water consumption if we're using wet cooling. So we have the potential though to actually produce water from our fuel, and without any significant additional effort in this case. Okay, so from a systems perspective, we're starting to look at some advanced integrated systems. So one problem with the fuel cell-based system is it's basically a steady-state system, and some people are working on trying to get them to work in a load-following setting. But for the most part, they're intended for steady-state baseline use. So what we're trying to do is integrate energy storage so that we can make it so we can follow peaks and troughs during an actual power demand cycle. Okay, so we're looking at compressed air energy storage. So this is the idea where you take air, and when you have extra power than you need, you compress it and store it in the ground, and then you can pull it back out as you need it to spin turbines and generate additional recovery. It's really fast, 7 to 10 minute startup, so you can actually match real-time loads very closely with this system. So it's nice. Couple are in operation. There's one more that was just announced last month to be constructed in Texas. So this is up and coming. But what's interesting is for the SOFC, the reason why we've chosen this is because we actually already have compressed air, spent air, as a waste product. So this is what we're going to store. Instead of taking fresh air and extra power to compress it, we can use our already compressed air as a waste product and use that. We need some additional power to compress it higher, but most of the work's already been done. And that's really, really nice because that just is an extra layer of synergy to do between the two. Okay, so here's an example. Here's for Ontario. This is a sort of power demand during the week. So this is 1 week last year in the summer. But we took a look, and we actually have good data for predictions. So at any given time, the Ontario grid operator puts out a 24-hour prediction, both in predicted price and predicted demand. And so we're using this in a real-time optimization framework to basically decide how much air do we compress or release based on our storage space and that kind of thing. Okay, so what we can do is this is that same week. So this black is the real demand. Red is what our system's doing. You can see our time steps here. Okay, we match it very, very closely using a reasonably sized compressed air storage system. Okay, and we chose this week to show you. We actually did it for the whole year. But when we overproduce, we do so gracefully. It's just a little bit and spread out over time. And when we underproduce, it's the same thing. It's sort of gracefully. We can kind of see it coming, and so we kind of smooth it out. Same thing down here on this side and then down here. So what this is basically doing is it's not only is it doing a good job of load following, but in terms of the grid itself, it's very nice in terms of handling how the rest of the grid will also respond. And you can tell it's optimized because here's our cavern pressure. So this is sort of our minimum pressure and our max pressure. So you can see during the week how our cavern pressure goes up and down. So when it's at the top, it's sort of maximum storage, right? And so when we just touch these bounds here, right, that means that's the best way we can possibly do it. Like, we're not getting stuck in waiting. We're just touching and moving on. So that's how we know it's optimal. In terms of carbon emissions, so we're concerned with both direct and indirect. So in this particular example, direct is what we produce, and indirect is what we have to buy. Anytime we don't meet demand and we have to buy power from the grid, that we're accounting for those CO2 emissions. And what's really cool is with our fuel cell compressed air system, our total direct and indirect is down to 0.02 million tons per year emitted compared to something, what's that, 2 or 3 orders of magnitude bigger. Yeah, 2. Just for this is regular classic natural gas combined cycle systems. Okay, so this is effectively, this is where it's almost 0. Our process is essentially 0, but we have to buy some off the grid. So even accounting for that, though, we're still very, very small. Now, I talked about this being a future system. And, essentially where we are in the scale-up is we're looking at roughly 60 kilowatt scale being manufactured right now for an individual, and we need hundreds of megawatts to do this in a municipal setting. So this is why we say it's decades out. But in terms of price, so here's an example. Right now you can get SOFCs at about $8,000 a kilowatt, and that is too much to make sense economically right now. But this is a plot from a recent DOE conference, and this is showing. If we took our technology today and mass-produced it, because right now these are not mass-produced, we could sell it in theory for $175 a kilowatt. Okay, that's in $2,000, the year 2000. This is about $250 a kilowatt in today's dollars. So they think it's just a matter of scale-up at this point. Okay, so this is the industry saying this. So we can, much more realistically hit this target just as a matter of scale-up. And if we use, in this case, I'm using $1,000 a kilowatt for my economics, which is so conservative, right, compared to that. We can look at the cost of electricity, and it's only a slight premium over existing natural gas. And we're looking at $0.25 cent a kilowatt for the carbon capture over at NGCC with carbon capture, and that's without a carbon tax. As soon as we have any kind of carbon tax in place, all of a sudden. Our system's looking really, really good. Okay, and that's from a pure economic circumstance. And you can see that the cost of adding carbon capture is really, really tiny. And again, that's because of the CO2 capture is really easy. So we can take a look, and we can see when is our system maybe more economic than another. So this is a map showing if the price of natural gas is this, the average lifetime price really, and the average lifetime price of carbon tax is this, which power generation system is better economically. So here, this is where we are now. So today, we're about 360. I think I checked earlier today. And then these are we have no carbon tax here, but EU we have about $9.85 a ton. It moves up and down. Alberta's at 15. Okay, so these are today regions. So here's a historical last decade average. Energy crisis, we peaked at 13 to 15 way on the side, but mid 2008 is around 10. Okay, so this is showing in this region the existing status quo is the cheapest. Gas is cheap, gas power is cheap, that's what's going to happen. But it doesn't take very much, really, to move into these regions where for purely economic reasons, having no concern about the environment, for purely economic reasons, the fuel cell systems are better. And these are all variants of the fuel cell system with different features I'm not going to get into. And if we look at expected market price, as soon as you start talking about carbon tax, $50 a ton, 40 to 60 is roughly when people think it needs to be to have actual change. So we're up in this region in any sort of future scenario that has real teeth. So this makes it look really, really good economically. Okay, so yeah.
So let me just pause you right here. I know Jamie has to go. I just want to give Jamie an opportunity to ask any questions before he had to take off. Jamie, are you still on?
I am on. Can you hear me?
Yeah, I can hear you.
Yeah, this is very interesting. You're looking at the SOFC. We've done similar work over here. One of the questions I had is, did you look at molten carbonate fuel cells? Molten carbonate tend to produce a higher purity CO2 stream, making them easier for CO2 capture and sequestration.
So you have to refresh my memory. The molten carbonate that uses the CO3 plus as the ion carrier, correct?
Correct.
Okay. So right now, Fuel Cell Energy is probably the leader in producing those, if I'm correct, also commercially.
That is correct.
Right. So this study with the SOFCs was actually born in working with Fuel Cell Energy on the SOFCs. And I won't really speak for them, but one of the main issues is that overall the system for the molten carbonate is not looking like it's going to be competitive with the SOFCs in the long run. And you know what? Oh man, I cannot remember the systems perspective, but I don't remember the molten carbonate having the ability to do this CO2 water separation on any of the same level. So I'm going to have to leave it at that because I can't remember the molten carbonate system.
Okay, that's fine. Yeah, just that there was a in addition to in the U.S. the fuel cell energy is the lead. Japan they actually did a demonstration looking at that with the molten carbonate.
Yeah.
So
And actually, I visited one of their fuel cell energies installed here in Canada. They have one just down the road in North York, so it's outside Toronto. And one of the issues was that the expense was just so much that they don't even turn it on because it's more to run it than to get from the power from it. So I don't want to poo-poo that technology, but the people that are making that are pushing their money into SOCs instead. So that's sort of what I'm going with.
I was just curious if you looked at that. So yeah, we've done similar analysis with the solid oxide fuel cells and come to some very similar results. So
yeah,
very interesting. Great. I do apologize that I have to leave. So
okay, thanks for joining, Jamie.
Okay, so and again, I mean, I did look at molten carbonate. I'm trying to think. It was back in 2008, so I'm struggling to say anything. I'm being recorded, right? So I don't want to say anything wrong here. Okay, so for polygeneration, this is the next section. So this is more an energy systems things, right? So this shows you more of the things you can do with the SOFCs, and we're going to talk about polygeneration. This is an idea where we take multiple fuels to make multiple products. And this term is sort of uncontrolled, so people will have a different definition than I do. The idea is maybe I want to do more than just natural gas, that maybe there's some kind of synergy with natural gas and biomass together, or with coal, or in some combination. Okay, and then maybe it's better to make multiple products instead of just one. And there's a lot of different reasons for that. One is just synergy exploitation. Like you can imagine something that's endothermic can get its heat from a waste stream that's exothermic in a different process, like a very basic level. The other area would be in agile production. So this is a sort of a very new bleeding edge research area, is the idea that you design your chemical plants to be agile so they can change what they make in response to markets. And that doesn't mean maybe you change your fuels or you change your products. And this could be like hourly changes or daily changes or seasonal changes, because the amount of money you can potentially make by responding to a market is so much, it's worth it to have the extra complexity. Okay, so we've done some studies into that. I'll talk about that briefly. But here's a very basic idea. So a thermochemical polygeneration process will take your carbonaceous fuels, convert them to syngas, so that's CO and H2 plus other junk, and in just the right blend, clean it up. You can add carbonless hydrogen or whatever, and we can use that syngas to then produce a bunch of different things. So we can do hydrogen, power, methanol, and all the alcohol products, Fischer-Tropsch, so that's all the gasoline, diesel, like synthetics, hydrocarbons from that route. So you can make almost any fuel that we use now that's transportation ready. So this is why it's an attractive approach. So here's an example using coal and gas to make liquid fuels and electricity. Okay, so here we have coal, or you could use biomass and blend biomass. It depends on how your gasifier is set up. Basically, we're going to use coal to make syngas with a low hydrogen content, and then we use natural gas to make syngas through reforming with a high hydrogen content. Okay, and basically this has a H2 to CO ratio of 3. This one has one of about 1, but we need a ratio of about 2 to do anything for transportation fuels. It's typically the sweet spot. Okay, so we make methanol and dimethyl ether and all the methanol-based products, diesel, gasoline, for example. And so we just blend the CO2 or the hydrogen lean with the hydrogen rich in just the right amounts to get the blend we need. And what we're doing with this process is we take this syngas and we would like to be able to change how much goes toward liquid fuels and how much goes toward electricity. So this is our electricity train. And we'd like to do that daily if possible. Maybe switch between a day mode where I make lots of electricity and a night mode where I make lots of liquid fuels. Okay, so for example, so there's a lot of different ways we can do that, and we'd like to be able to blend this and have that sort of flexibility. Okay, maybe we change how much methanol and diesel and gasoline we make. And we had some prior studies I did with a student at MIT, and we basically quantified that if you can do something like this in the petrochemicals industry, And you can just respond, add a little flexibility and respond to market conditions. You're looking at $1 billion in net present value increase, essentially real profits over the lifetime of your plant. And that's just from meeting market demand and nothing else. So that's the kind of potential we're talking about. But what's nice is even this you can improve with the SOFCs. So if, for example, we instead of using, here's the old one, our gas turbines to produce electricity like syngas turbines, we can use fuel cells because you can use syngas in a fuel cell, the SOFCs. All right, and we do this where you know, we keep our air and our fuel separate because we can do that with SOFCs, but we can capture basically 100% of the CO2 rather easily in this train and compress it. Okay, so our electricity train we can make CO2 free, and we still have this sort of purge gases from our methanol and Fischer-Tropsch synthesis, right? Because you're never going to get it all. You're going to have some extra nitrogen, that kind of thing. So right now combustion is typical. We'd like to replace that by just moving that to our SOC because these are fuel flexible. Okay, so what we're looking at is a system where all the carbon, so these fancy streams are carbonaceous, right? The carbon has nowhere to go, basically, but in the ground when you do this. So you're looking at 100% carbon capture, making liquid fuels and power, and we want to be able to do this where we change this stream here, like how much we go this way or that way, to change our product mix. So right now, this is sort of an advanced thing we're working with the DOE. We're doing some studies on this section here. How far can we take it, kind of thing. Okay, so it's really neat. So this, just from a systems perspective, the SOC just lets you do so much cool stuff. Here's another example. So this is a different systems integration idea. It's the idea of using, all right, gas reforming as a cooling mechanism for coal gasification. So here, if we go back, what we do in this gasifiers, these are ultra high temperature, like 1300 C, and we need to cool it. And right now, radiant cooling is one of the main technologies where you just basically raise steam. Okay. And that's good, but a better way to do it is actually to take steam and natural gas, and in your radiant cooler, this is filled with like a reforming catalyst. And then what we can do is we can still provide cooling, but this is highly, highly endothermic. So it absorbs heat, and the product instead of steam is hydrogen-rich syngas. That's a much higher exergy, higher value product. Okay, and then what we can do, we take our hydrogen-rich syngas, we just blend it with our hydrogen lean coal syngas, right? And now we have a system that integrates these two steps. So this is really, really cool because now we're integrating one of the major areas of exergy destruction, or just energy waste, basically, by doing this. So as a result, we have a system that looks like the ones we had before, but now it's just basically more efficient. But we get that because of the dual fuel. So not going over these plots too much, but we can control how much electricity we make, and we can look at the different designs and how efficient they are. And basically, you're looking at 3 percentage points more efficient by using the two separate fuels than one alone. Okay, and when you have carbon capture, that's where you're really at, SOCs and carbon capture. You're up to 10 percentage points more efficient for the same product mix, the same portfolio, just from using this kind of integration. Okay, so that takes newer technologies and developments, but this is what we're talking about. This is what we can do in the future. This is where we want the research to go. So here's another example of how does this work economically. Okay, so here we have a plot showing our optimal plant designs based on economics as a function of market prices. And we have on one axis the Henry Hub spot price of natural gas, and then we have wholesale gasoline prices. Okay, so each colored region is a different design. So this one says the most profitable thing at these high gasoline prices and low natural gas is to make as many liquid fuels as you can, and just using natural gas. Okay, and some coal in that sense. But then down here we have coal only with maximum electricity and carbon capture and so forth. And in between we have these blends. So in this red triangle, it's optimal to do our sort of integrated system with half electricity, half liquid fuels, or 56% in this case. Okay, so it's really interesting how the product mix and your technology is optimal depending on the market conditions. Okay, so here we are in the States today, and Canada's a little higher because the gasoline price is a little higher. This is wholesale, not what you find at the pump. But we're sort of in this region. But the point is we've been all over. So the idea of the flexible system like this is we want to sort of target the middle and then adjust as we go over time as the seasons change. Okay, and that's sort of what we're looking at for the agile systems. CO2, of course, another issue. If we take a look at electricity price and CO2 price again, so fixing the others, you can see the different regions at stake and how much these parameters are in there. And you can't really predict these before you build. Like, you can try. So that's where the agility comes in, right? We'd like to be able to move around. Okay, so next I'm going to talk about another idea. So we're starting to expand our horizons a little bit and just, we're looking at individual pieces of equipment that might be better, and we're looking at individual systems. So now we're looking at, call it nuclear polygeneration, but it's sort of saying, okay, we have this coal and gas integration, and that's promising. Let's look at nuclear. So this was an idea that was sent to me from someone formerly at General Atomics, and so they're working with a special type of nuclear reactor. It's a 4th generation one called a Modular Helium Reactor. So this is showing here, and basically it's just high temperature and helium. High temperature heats helium, and that goes through a Brayton cycle, and it's pretty classic from our perspective as a chemical engineering. Okay, so what we're looking to do in this case is making liquid fuels out of coal, gas, and nuclear energy. So one way to do this is to use that high temperature heat generated by nuclear reaction, not for electricity generation, but to drive natural gas reforming. Now, this is not in itself a totally new idea, because people have been looking at nuclear heat to make hydrogen through this route. So we're just not making hydrogen complete, we're just making hydrogen-rich syngas, so just the first step, basically, and then integrate into a system. Okay, so this is not that crazy, because people have been looking at this for 20 or 30 years. So this is just a system where we take natural gas, coal, and nuclear heat. We have CO2 removal. We can get 100% of CO2. We get our proper balance of syngas, and we can make Fischer-Tropsch liquids. So here's naphtha, gasoline, and diesel distillate. Okay, so they're precursors to your transportation fuels. We're looking at different kinds of configurations, how we handle recycle, that kind of thing. But basically, this is how it works with the nuclear integration system. Is right now you basically have your modular helium reactor. You get this high temperature helium out at high pressure. That spins a turbine for power, and then you sort of then you just cool and recompress and recycle, right? So that's a basic power cycle. We're basically proposing adding a reformer here, so that helium has heat exchange basically with our steam and natural gas, or reforming section. And then we just have a lower temperature helium to produce less electricity and operates at lower temperature. Okay, so we can basically look at these two and understand the effects of how much electricity we sort of sacrifice to get more liquid fuels. Okay, but it's not that huge of a change, right? These are just tubes, just a heat exchanger. Okay, so when you look at CO2 emissions, these cases are just different versions of different design options, and this is a coal gas to liquids, coal and gas to liquids, and this would be coal gas and nuclear to liquids. So CTL is just coal to liquids, and that's sort of traditional, like South African Sazol, coal to liquids. Okay, and here what we're looking at is our direct and indirect. So our indirect emissions are black, so if we have to buy any additional electricity to run our process for making liquid fuels. Coal to liquids, 12.5 tons per 1,000 gallons of product, and our coal and gas cases are in the the 4 to 5 range. But with nuclear, even without carbon capture, we're only at 2.7. So we're looking at an order of magnitude drop in emissions just from coal only, and half from coal and gas, just because we're using nuclear energy, and that displaces fossil fuel. Okay? So even if we don't do carbon capture, we're still way better off. And with carbon capture, there are options. We can go basically down to 0. And that's what's really cool, is we're making liquid fuels again using 3 different sources, and we're going down to 0 emissions from both direct and indirect. So these are, the indirect is purchased off the grid, so you have to account for those. But where you can really see what happens here is in the carbon efficiency. So the carbon efficiency is the percentage of carbon atoms in the feed that end up in the product. Okay, so what that means is a high carbon efficiency, you're using your carbon atoms to make as much product as possible, and as little of those are burnt and wasted as CO2. Okay, so for coal to liquids, all right, your carbon efficiency here is 33%. All right, and then the rest here is, in this case, this is sequestered if we have carbon capture, and this is what's actually emitted. These are for our carbon capture cases. But if we have our coal, gas, and nuclear to liquids, 72% of the carbon in our basically our coal and our natural gas ends up as diesel or gasoline. Okay, and we're only having to sequester 24%, which is much lower than all the other options without it. So not only do we produce less waste, so there's less to sequester, but this is an incredibly, incredibly high carbon efficiency. That's really one of the exciting things. And what we're really doing is we're inventing a way to export nuclear energy in a non-proliferation form. Okay, so there's one mine in Saskatchewan that has, I think, 250 or 300 years worth of uranium at our current rates. It's incredible. All right, so we're finding a way to take that energy and sell it as just diesel or gasoline, which we can definitely do that cross-border. That's not a problem. And up to 20% of that energy in the diesel and gasoline came from the uranium. So it's a major contribution, and it's a way to use our resources in a different way that sort of gets around that sensitive issue of proliferation. So there's a lot of really, really cool stuff that can come out of it. And again, we're looking at market uncertainty. Here we have gas price and CO2. Here we are in Alberta right now, U.S. over here. So there's a carbon tax in Alberta. So the optimal here is a coal and gas to liquid system. This is coal, gas, and nuclear design number 1. This is a different variant. So we're actually really close, right, to that line once it starts to be. This is just pure economics. You know, forget about environment, just pure economics. So even from that perspective, there's good reasons to do it. Okay, so I'm going to finish up pretty soon. I'll just close with chemical looping. And this is another major technology that is up and coming, and it enables all sorts of stuff. So it's sort of a direct competitor with the solid oxide fuel cell, in the sense that they both try to do the same thing, where they take your fuel and they want to basically oxidize it without nitrogen. So what they do is, instead of air, they use nickel oxide, or some metal oxide. In this case, I'm looking at nickel. All right, and what that means is the nickel oxide, in this case methane, we get our water, CO2, lots of heat. Okay, and so this means our heat is released, and the energy goes into the hot exhaust here, and also into the hot nickel. And this means our CO2 water, again, is really easy to separate. That part's easy. And then the second section is our nickel gets oxidized in the air. That produces more heat, right? And we basically get this like high pressure, high temperature depleted air that powers some turbines, and we have some steam heat recovery in our plant. So this is a way of doing easy CO2 capture. So it's an enabling tag. And there's many variants of this. So like, here's one for iron. In this case, we take our fuel, and instead of, we use this heat to make hot iron oxide, a different oxidation state here, and we reform steam. So instead of using this for power, we basically strip the oxygen off the steam to make hydrogen, and then we recycle iron oxide that gets combusted in air to regenerate. So what we're doing is we're using the energy of the natural gas to produce hydrogen. So we can burn that or use that as a fuel stock. So these are cool because, again, all the carbon ends up being easily capturable. Okay, so I'm not going to get into this too much, but we're looking at Polygen systems now using different kinds of iron oxide loops, nickel oxide loops, different kinds of gasifiers, optional natural gas integration, optional nuclear heat integration. And basically, without going into the details, this is a system with 100% carbon capture. And now here we just chose methanol and DME as our products, but you could use this for any kind of transportation fuel. And it's neat because what this tells us is, like, even if I use just coal, it's much more efficient than, even just for power, than all the classic methods with 100% carbon capture. And we can actually add natural gas at whatever proportion we want. So it's very scalable. We can determine how much we want to use of the different kinds, so it's very flexible from that perspective. And I can choose how much liquids and power I make in the mix. So for example, I can choose half power, half liquids. Okay, so this is really cool. So this is an ongoing work. But this is an example of how that enables some really interesting systems. So I'll just end it there. Basically showing the different techs that I think are really going to change things. We have the fuel cells is one of them. Compressed air storage and many kinds of energy storage are interesting. In this case, we're just doing like a compressed air, but integrating different major techs like gasification, reforming, and fuel cells. Nuclear energy could play a huge part, and then this chemical looping opens up another whole area of systems that we could possibly do. And then I'll just close acknowledging my team. I have a lot of undergraduates that contribute to parts, but we pretty much only saw the bottom half of these guys. But I didn't talk about biofuels and that kind of thing today. I'll be happy to another day. And with that, I'll close. Thank you very much.
Okay, great. Well, thank you, Tom, and I'll go ahead and open it up for questions. Just remember when you go ahead and unmute your microphone if you'd like to ask a question. And if your microphone isn't working, you can put your question into the chat window, and then I'll go ahead and read that to our presenter. So I'll go ahead and open it up to any questions that you might have from any of the audience here.
Yeah, I have a question. This is Jose. So you mentioned here that you do some of your, at the beginning you said that some of these models or optimization was on steady state models. I mean, are you doing any dynamic models over like long period horizons, or how do you handle that?
Okay, so the first part was muddled, so I heard you asking about whether I'm using steady state or dynamic models. Are you asking about a specific system?
Well, just kind of like differentiating the first part versus the latter part, where I saw like a bigger system with a lot of integration. You know, wanting to see if you doing any dynamic optimization on those.
Okay, I think I can answer your question succinctly. So for this example, this would be a steady state at this point. So what we're looking at right now is just the steady state, and you know, for this particular example here, these are individual steady state processes that we design ahead of time. We haven't looked at the dynamics for this particular system of how do we switch between them. That's sort of the next step. Some of our other systems, like this one, the modular helium, the coal gas, nuclear, those are all steady state systems that we're doing right now. And when they look good enough, then we look at the dynamics. So this here, for the coal and gas integration, we actually have an entire research program we're doing with Imperial Oil right now on the dynamics. So we're building dynamic models because what we want to do, we're very interested in doing this dynamically with maybe how long does it take to transition between different steady states. So we are building dynamic models for this section, which is not easy because gasification is an art form more than a science in many ways. And then for the fuel cells, these are all steady state at the moment. But what we're doing is we have a pseudo-steady state for our this sort of thing. So we have these sort of 1-hour time intervals, and we're breaking this down a little bit. We do this for the entire year because the transition for this particular case is really fast. So when you have a system like this, all of this is actually all steady state all the time, all base load. So we only need to do one model for this. And the storage part is the dynamic part, but the dynamic part is so fast because it takes 10 minutes just to start from 0, but just to tweak up or down with the load, that's just quick. So this is really, really fast, so we're not concerned about that. What else? There was one more. Oh, yeah, so for the last one, we were talking about with the Department of Energy, we have this, oh, shoot, which is the one? We're looking at, I'll bring it up, it's in the next section here. This one, where we're using dynamically changing our electricity and our fuel gas amount. Then we have, so this purge gas also changes with time. So we have sort of two streams coming together. We're doing this experimentally, like it's called the hardware in the loop system. So it has parts of it are experimental, like the air compressors and the turbines and the combustors. And then parts of it are models, like the SOFC model is a dynamic model. The reason is we don't want to break an actual SOFC, so we're using a model and forgetting to break that model over and over again to see if it'll work. So the answer is we do both. We're trying to do everything, and we'll never do everything, but different parts.
Okay, thanks.
Okay, great. Thanks, Jose. Okay, any other questions? Be sure you unmute your microphone if you want to ask a question. I guess I have one question. The nuclear integration looks very interesting. Do you have to have so if you had the nuclear plant close to the other facilities, are there any other opportunities for integration of perhaps waste heat or other? I guess you do need them close together. Is that right?
In this particular case, yeah, the nuclear plant would be next to the coal. Because you're basically literally bringing in your gas from your gas plant, right, and you're integrating with your nuclear plant. So these two would be close together. The other integration, if you had heat integration between the two, you could. All of our designs have their own sort of internally optimized heat network. But yeah, there's other potentials here. However, this is already sort of stretching it in terms of what people want to do with nuclear. Like, nuclear is not something you can innovate in very quickly. It takes a long, long time for people to accept things. So we're going to stick with this one thing. See if that catches on before we move on to any other integration that way.
Okay, so just initially you're proposing just the energy integration, but there may be other opportunities.
Yeah, and there always are, you know, and there's so much going on with these plants, right? Every heat exchanger is an opportunity for something.
Yeah, that's right. Okay, great. Any other questions? Okay, well, great.
Well, if no one else asks more questions, I have a couple of other questions.
Okay, great, Jose.
And I guess I can have a lot of questions, but this is very related to kind of like the work that I'm doing with you know, CHP optimization and planning, which I'm finishing up my work. So I did see in the beginning, you know, you mentioned, and everybody does, and you know, uncertainty and risk. What have you done to quantify the uncertainty and apply it into the optimization, or have you done any of that?
Okay, so again, there's the connection's not so good. Let me reiterate the question to make sure I understand. You're asking me how I handled uncertainty in the real-time optimization. Is that correct?
Right, right.
Okay, so you're talking specifically about the uncertainty in the predictions of price and demand for the fuel cell system, right?
Right, right. I mean, I guess that's what one of your kind of like your stochastic variable that you input into your model, and
right. So yeah, so what we did, or I should say my student did, because I didn't do it. But what we did is we have every hour we get a new profile for the next 24 hours. And so what we did is we went back and we looked at resimulating this over and over again, like a Monte Carlo analysis, basically, by saying, okay, this is the profile we get, and then just sort of making sure that, okay, if we get a slight deviation, like these are all deviations from our mean, so like this is our real profile, and based on historical data, we know that we got about 6% uncertainty range, standard deviation kind of thing. So we can just go back and rerun this over and over with different instantiations of that uncertainty from the real. And so what that does is that says, okay, like if we're erroneous, and that error grows with time. You can actually that's the maximum that it's really quite good in the next hour, for example. So we do this over and over again, and based on that, we can determine to make sure we actually get performance, and we're able to, you know, plot how well we match and our profit as a function of how good our predictions are and all that. And even when the predictions are not that great, it still works really well. So we have this is this manuscript's been submitted, so hopefully you'll see that soon. Those details.
Okay. Yeah. So I particularly in this model, in this case, like how large is your problem that you have to solve each time?
That's correct. Every time step, it's solving an optimization problem. So the outputs of that optimization are what you do right now, and then what do you think you're going to do for the next 24 hours every hour. And then you just redo that every hour. So you're just constantly resolving. The optimization itself only takes about 10 seconds per time step, so it's not a problem.
Okay. And how many and the time step you do like in whatever 24 hours?
Yeah, and we actually looked at the the effect of how far your horizon is. So if you have 1 hour or no hours up to 24, we can tell you how good your system will be. 24 hours is about right because it encapsulates one cycle. That's about as best you can predict anyway. And so, you know, we have plots. I can't remember what they are right now, but they basically quantify exactly how good it is with that prediction time. So you can you can adjust it, and this shouldn't matter if it's Ontario or someplace else, right? And we looked at it from both a performance perspective and just a profit perspective. And it's really interesting. If you do the load following, you can get really good load following matching, and if you do profit, you get something completely different. Like you don't care at all about matching, and you just try to make more money. So that you get completely different results doing that. So it's kind of interesting to see how that plays out.
So that mismatch in the model towards the end of the week, is that basically due to the higher uncertainty? Is that
the mismatch on the screen, like here?
Yeah, like right here at the beginning of the model, I see it has a closer match to the actual versus at the end. You see, there's more mismatch between.
Yeah, so this is a mismatch of what was actually produced in the demand, and this is actually a result not of the model, not like or suboptimal results. This is a result of storage space. So in this case, we're overproducing because we actually are going to run out of space. We can't actually add any more to there. Okay, so this dashed line is our baseline plant. So this is the parts of the plant that we don't change ever, the fuel cell parts. And so eventually we get to a point when we can't store anymore. So we just have to overproduce. And then on the other end, this place we can't quite produce enough. All right, and so we run out of storage. And so we're sort of gracefully managing our low storage here. So this, like our plant is scaled to be like 720 megawatts, but we can provide up to 850 at any given time because of that storage, right?
Okay. Thank you.
Okay, great. Any last question that you have? Any other questions from the group? Okay, great. Well, thank you so much, Tom, for your presentation. And what I'm going to do is let me just go ahead and share my desktop. I'll just give an overview of some of the other presentations coming up. Next week, we have prospects and challenges for olefins production from 4 industry experienced experts here that over 100 years of combined experience in optimization of olefins plants. We're going to be talking about hydraulic fracturing and the prospects and challenges for olefins production, for optimization and control, and then on down the list. So we have some more every week. And the other thing I'll mention too is we're also looking for additional presenters. So if you feel like you have some material that you'd like to present, we'd like to invite you to send me a title and a potential date when you'd be willing to present. And but thank you, Thomas, for presenting today. I thought that was very stimulating discussion and very exciting research results that you have.
Yeah, thanks a lot.